Can we escape Earth's problems by colonizing other planets? It's a question that has fascinated writers, scientists, dreamers, and explorers for centuries. From the earliest tales of celestial voyages to modern-day missions to Mars, the idea of leaving Earth behind and starting anew among the stars has captured human imagination like few other dreams. But let's take a moment to ground this fantasy in reality. What would it actually require to survive on worlds so hostile they make our planet's harshest deserts seem like paradise? What tools, what technologies, and what adaptations would we need to make alien environments habitable, not just for exploration, but for life? Extreme radiation, toxic atmospheres, deadly cold, crushing pressure, unpredictable weather, and the ever-present threat of the unknown. These are the realities we would face beyond Earth. Could the answer lie not in building massive domed cities or terraforming entire planets, but in reshaping ourselves? Not biologically, but mechanically. Could advanced exoskeletons, powered wearable machines, be the bridge between fragile humanity and the brutal conditions of space? Because the truth is, once we leave Earth, we are no longer in control. The moment you step onto the surface of another planet, you're not just a visitor, you are an intruder, and the environment will respond accordingly. No breathable air, you suffocate. Intense solar radiation, you're cooked from the inside out. Sub-zero temperatures, your blood freezes. Even reduced gravity poses a threat to your bones and muscles. Surviving off-world isn't just about bringing food and oxygen. It's about engineering our survival at the most personal level, our bodies. That's where exoskeletons come in. Not as simple tools or gadgets, but as comprehensive life support systems. Imagine a suit that doesn't just protect you, it becomes part of you. Not in a dystopian cyborg sense, but in a seamless fusion of man and machine. A synthetic skin that strengthens your movements, regulates your temperature, shields you from radiation, keeps your blood pressure stable, and supplies oxygen while removing CO2. It doesn't just keep you alive, it enables you to live, move, work, and adapt in places where humans were never meant to exist. Right now, on Earth, we're already seeing the rise of exoskeletal technology. Hospitals use them to help stroke victims walk again. Construction sites deploy passive suits to reduce injury and fatigue. Military prototypes enhance soldier endurance and strength. These early iterations are clunky, slow, and limited, but they're proof of concept. And with rapid advancements in materials science, robotics, AI, and biomechanics, the exoskeleton of tomorrow may be as revolutionary as the spacesuit was to the Apollo era. But the exosuit of the future won't just be a spacesuit with gadgets. It will be a full-body interface between human intention and environmental hostility, a wearable habitat, a mobile command center, a personal robot. Picture a next-generation exosuit that integrates muscle amplification, AI-driven reflex enhancement, radiation shielding, and atmospheric sealing, all powered by a lightweight, renewable energy source and constructed from smart, reactive materials. Sounds ambitious? It is, but so was landing on the moon. Now let's take a step back. Why would we need something so extreme? Let's look at Mars. Mars is often our first candidate. It's close by, has polarized caps and days similar in length to ours, but it also has a paper-thin atmosphere made mostly of temperatures that can plummet to -125 degrees Celsius, and surface radiation levels up to 250 times higher than what we experience on Earth. That alone would render a human unconscious within minutes without protection. And that's just Mars. Venus, beneath its clouds, has a surface temperature hot enough to melt lead, an atmospheric pressure nearly 100 times that of Earth. Even Jupiter's moon, Europa, with its suspected subsurface ocean, requires us to survive in vacuum-light conditions on the surface with extreme radiation exposure from Jupiter's magnetosphere. The message is clear. Anywhere we go in our solar system is inherently hostile. There's no shirts, leave environment waiting for us. Colonizing space means meeting these conditions head-on with technology designed to extend the boundaries of the human body, which brings us back to the exoskeleton. An exosuit for space colonization would need to do much more than support movement. It would need to become a wearable ecosystem, and every aspect of its design would need to be focused on energy efficiency, durability, and adaptability. So how do we even begin building something like this? First, let's talk power. Traditional spacesuits rely on portable oxygen tanks and battery packs, but an advanced Exosuit would need an integrated power source capable of lasting 4 days or even weeks, preferably rechargeable through solar panels. All thermal gradients in the environment. Imagine ultra-thin, flexible solar fabrics woven into the outer layers, constantly harvesting energy from sunlight or artificial lamps inside a habitat dome. Internally, the suit would need layered systems to manage temperature, moisture, air composition, and pressure. Think of it as a living organism, breathing, sweating, adapting. Small-scale heat pumps, co-scrubbers, and biosensors would all be embedded to maintain internal equilibrium. Then there's the question of shielding. Cosmic rays and solar flares are lethal over long durations, so the materials would need to be embedded with radiation-absorbing components, perhaps boron nitride nanotubes, hydrogen-rich layers, or new polymer composites capable of dispersing energy without adding massive weight, and weight is key. The suit can't be a tank. It has to allow free motion, agility, and responsiveness. That's where smart materials come in. Fabrics that stiffen on command, microhydraulics that amplify movement, AI-controlled actuators that learn your walking pattern and assist rather than resist. This vision of an exosuit isn't just protective gear. It's a hybrid between armor and organism. A device that doesn't just shield you from Mars or Europrit, empowers you to live there, work, build, explore. But what makes this concept even more exciting is the potential for augmentation beyond survival. An advanced exoskeleton wouldn't just protect, it would enhance grip strength, better visual processing through integrated heads-up displays, even neural-linked reflex systems that reduce response time in emergencies. Think of it as merging the best of astronauts, engineer and athlete into one versatile being. Colonists equipped with such exosuits wouldn't just endure, they'd thrive. Imagine setting up solar arrays on Titan's icy crust door, navigating the jagged lava plains of Io, not in bulky suits that limit motion, but in agile sensor-rich exoframes that respond instantly to your intention. These suits could carry tools, extend arms, analyze samples, and provide real-time diagnostics. No need to call him back up or retreat to a base for minor issues. The exit suit becomes your assistant, your protector, your multi-tool. And as missions expand in duration, months, even years, these suits would evolve into personal ecosystems. They'd monitor biometrics 24/7, deliver medications, regulate circadian rhythms with light exposure, and even adjust tags or feedback to combat sensory deprivation. With AI-driven behavioral algorithms, the suit could detect psychological stress or fatigue and suggest interventions. You're not just wearing a machine, you're collaborating with it. To truly unlock the exosuit's potential, however, collaboration is key. Public space agencies, private aerospace companies, and universities around the globe are already laying the groundwork. Initiatives like NASA's Soft Robotics Lab, MIT's Biosuits, and ESA's Advanced Concept Team all pushing boundaries. Meanwhile, private innovators, Boston Dynamics, Sarcos, and others are developing commercial exoskeletons for industry and defense. Combining these efforts for planetary colonization will require not just innovation, but international cooperation, sustainable funding, and open-source sharing of breakthroughs. And this technology won't only revolutionize space. Imagine disaster relief teams equipped with ruggedized exosuits navigating collapsed buildings after an earthquake, or construction workers lifting heavy loads with minimal strain, or deep-sea researchers operating in crushing depths. The applications on Earth are as transformative as those in orbit. Still, even with all this promise, we must address the deeper implications. Who will own this technology? Will it be available to all settlers, or only the elite? Will it change how we define humanity? Could reliance on exosuits dull and natural abilities over time? As we move closer to this future, these ethical questions become central. Colonizing other worlds may offer us a second chance, but only if we do it right. So where does this all lead? Toward a vision of the human explorer, not as a fragile being clinging to survival, but as a resilient pioneer equipped to thrive in the harshest environments known to science. A human merged with machine, out of necessity, alone, but out of ambition, curiosity, and the unstoppable drive to reach farther. This is the next chapter in human evolution, not just a leap across space, but a transformation of what it means to be human. The merging of biology and technology, of willpower and machine precision, forms the frontier of our new species identity. A being no longer confined by terrestrial limitations, but one defined by adaptability and resilience. And the exoskeleton, it's more than protection, it's more than augmentation. It's our vessel into that future, a testament to our refusal to accept boundaries, our armor against extinction, and our key to turning the cosmos from dream into destiny.